Welcome everyone. Thank you very much for joining this emissions analytics webinar on exposures to particles and volatile organic compounds across multiple transportation modes. Put simply, different journeys from London to Oxford as a way of getting a first pass on what the exposures are across trains, buses, cars and the like. So the format of today will be, I'll speak for about half an hour or so, and then there will be time up to half an hour for questions as well. Please put those in the chat function and I will read them out and tackle them as best I can. The presentation and the recording will also be available afterwards for anyone who would like to request it. And of course, please get in touch with us if you have any additional questions afterwards. So, diving in, firstly, it's always worth recalling what emissions analytics is all about. And we've now been going for over 11 years, and our commitment is to understanding what goes on in the real world. In a sense, the counterpoint to official regulated values, which obviously play a crucial part in the market, but don't necessarily always get to what is really going on in reality for real consumers. So that's what drives us every day. And we're headquartered in the UK, as many of you may know, but operate all around the world. Our independence is crucial to what we do. We test lots of vehicles of different shapes and sizes, over 2,500 so far. We're best known for our work on tailpipe emissions, but that's broadening out. We're doing a lot of testing on tyre wear emissions and, relevant to today's presentation, vehicle interior air quality tests. And we've tested already well over 100 different vehicles. We pay the bills. Our business model is around creating databases containing this information and making that commercially available. And to that end, we work with people up and down the supply chain, from vehicle OEMs to fleets and media and suppliers and the like. I'm personally chairman of two SEN standardization workshops, Workshop 90, which was on NOx from the tailpipe, but relevant today was SEN Workshop 103, which is about ingress of particles into the vehicle cabin. And I'll say a little bit more about that later on. And I'm also honorary research fellow at Imperial College in London. So specifically for today's content, we will cover what the objectives of this particular work were, the measurement equipment, the test route, and then get into the results relating to the VOCs, particles, CO2. And then crucially as well, this does not pretend to be the final word on any of this, it's really a first word on it. And so where this points to for future work is really important, and hopefully it'll inspire some additional work in this area. So in terms of the objectives, well, first of all, the project was very kindly funded by the Transition Clean Air Network, and which is a UK-wide network led by University of Birmingham, many universities and other partners involved. And I would encourage you to check out their website and find out the breadth of the great work they're doing. Ultimately, the funding for this comes from the Natural Environment Research Council in the UK. So the question in headline was, what is the cleanest way to get from London Paddington to Oxford city centre in the UK? Cleanest in terms of the exposure to pollutants of the traveller. This journey is about 85 kilometres if you go point to point in a straight line, almost due west. Now, some of the journeys we look at today are much longer than 85 kilometres, particularly the public transport ones. But that's to give you an idea. It's starting in a city centre, ending in a city centre, through a lot of countryside. And to be really clear, this was not designed for multiple repetitions and for testing the statistical significance between different cases. This was, by its nature, a first and relatively limited scope study. but it was designed as a first pass to see where potential issues exist, where issues don't exist, to help guide further activity and spending, investment, regulation, whatever, within the transport infrastructure to reduce the exposure of pollutants to the travelling public. These measurements were all made in May 2021, so not in the depths of the winter. And you'll see there the various different modes that we covered across 5 days. So it is 2 different types of train, an electric diesel hybrid one and 2 diesel ones making up one journey. The London Underground electric train, a hybrid bus in Oxford, I beg your pardon, 2 types of passenger car, a diesel internal combustion engine and an electric vehicle, and a diesel coach. And the exact models there are listed. But ultimately they were all point to point. The only variation from that is where we added in some walking and cycling as the last leg from, say, Oxford Station to the city centre. So not exactly the same journey, but allowed us to gather some data as to what the real world exposures were of cyclists and pedestrians in urban centres. So we're testing for volatile organic compounds, particles, mass and number, and carbon dioxide. And for that, the range of equipment we used is, on the VOC side, we were collecting using the thermal desorption tube shown, using primarily pumped sampling. So this coupled with a pump of known milliliters per minute on the traveller, affixed to the clothes, and made the journey. And then at the end, capped the thermal desorption tubes and then put it through this 2-dimensional GCMS system from Sepsolve and Marks International. Now, 2-dimensional is crucial here, and I'll come on to that in a bit, to give the separation and resolution on all the different compounds that we saw. For the particles and carbon dioxide, we used a very neat, compact detector from NAQTS in the UK, which has a CPC for measuring particle number, a laser scattering device for particle mass, and a NDIR for carbon dioxide. So, well accepted techniques, but packaged in a neat box, which was then carried either in a suitcase on public transport or in a trailer or backpack for the active travel. In terms of the test route, and this will all be available in a paper we will be publishing shortly. And here pictorially you can see and color coded essentially the various different routes. You can see it wasn't all direct, and it did involve crossing London on the London Underground, and then within Oxford city centre, say from the train station to the city centre, always it was ending up at the same point on Oxford High Street. So, moving into the results, I put up here, first of all, just to get, so we understand what we're talking about in terms of VOCs and what we've measured. When we pass it through the GCMS, we get a chromatogram, which represents all the organic compounds that we have picked up. And this chromatogram shown is from the hybrid train, the one which goes direct from Paddington to Oxford. Now on that, each of those peaks represents an individual organic compound. And the 2 dimensions you can see, the main dimensions, are time dimensions, which is the separation in the columns. And 2 different columns, a polar and a non-polar column. Essentially, we pass down the mixture that we gather, and in that column, the lighter compounds move faster down the column and the heavier ones more slowly, and so they come out neatly in order. And from that, we can then identify what they are using the generally available NIST spectral library, looking at the spectral patterns from the spectrometer. The height of the columns you can see are the height of the columns are an approximation to the prevalence of that compound. So the higher the peak, the the more it is. It's essentially a voltage on the mass spectrometer, so it doesn't directly correlate with the mass, but it is what's called a semi-quantitation. And we can see hundreds of compounds, and that can be rather bewildering to analyze. So we can actually then collapse that down into different functional groups, which have different characteristics, severities, from the alkanes group, which typically has bad effects on various human organs, through terpenes, which are less problematic for health but can have some air quality issues, through to the more concerning aromatics and nitroaromatics, which are often carcinogenic. Obviously, throughout this, when we talk about the potential toxicity of VOCs, obviously toxicity only exists at certain actual concentration exposures. What I'm not saying through any of this is that any of these compounds are at levels which are causing immediate acute human health effects. But nevertheless, we need to be very mindful of chronic effects, long-term exposures to these sorts of compounds. So here's a summary of the VOC exposures across all those different modes, using those functional groups, but also doing two other things as well. Looking at, because obviously in different modes of transport, they take different amounts of time. Some are faster than others to get to the destination. Also, during that journey, the traveler is having to do different level of exercise, if you like. Obviously, cycling is the most active, walking is pretty active, sitting on a train is the least active, and sitting in a car is pretty sedentary. So actually the degree or the rate of respiration and the duration of the journey needs to be factored into the concentrations being observed, which are average concentrations, in order to look at the total exposure. So the total exposure is the totals column showed. So if we look down that, we can see immediately that the highest total exposure was via the coach. And with a particularly high contribution from the alkanes group. Firstly, it's high, you can see, not because of the level of exercise during the journey, but because it's very slow. That journey from Paddington to Oxford is a London Underground journey from Paddington to Victoria, but then the Victoria to Oxford leg is slow. And it's obviously through congested cities and on the motorway, on the M40. And so the high alkanes exposure is likely to be due to pollution from other vehicles along that journey, which is very slow, relatively speaking. So whereas if we contrast it with something like the on foot or by bicycle, particularly if we take the bottom row, the bicycle, that has relatively low total exposures. Now that's interesting to observe, in that when we look at the real-time information in a minute, we will see that the cyclist is exposed to significant peaks when they drive past, say, a dirty vehicle. However, there are long periods in between that have very fresh air, which brings the average well down. So that's the high-level figures. But just to show the power of the two-dimensional GCMS approach, we can actually look at the individual compounds and their potential source and their potential health risk. And this gives a level of color, of depth, that helps understand what is going on. So across all the different modes, we identified 275 distinct organic compounds. And this table here shows purely the top 12 of those. And I've circled a couple just for note. So nonadecane, for example, and you can see, you know, in which modes of transport it was particularly prevalent. This is likely to be sourced from diesel combustion fumes. Not necessarily exclusively, but that is the most likely source. And the effect of inhaling nonadecane is lung irritation. And we can see that it is mostly prevalent, or the highest concentrations of nonadecane were on the electric car and the coach, both of which were road transportation. But if we look down the list beyond that one, which is probably a combustion emission, a lot of them come from what I've denoted as personal care products. Now that is most likely to be deodorants, shampoos, perfumes and the like. So fragrances and alcohols and other emissions from essentially other people, but not necessarily exclusively. It can also be from the interior fabric of the vehicles as well. Now, they typically do not have such problematic human health implications, and stands to reason if it's shampoos and perfumes. But as those are released into the environment, then in the longer run, likely to have, or their potential health risk is more to the aquatic environment and fish. So we must be conscious. This isn't just about human health air exposure. It is the wider sense of environmental impact. So this is a list to study in your own time. And the list, as I said, is 275 compounds long. It's a real depth, and it must be emphasized that in talking about these exposures, these are potential health exposures. This needs to be put together with additional research as to what is actually toxic at what concentrations. Taking this notion of source apportionment, i.e. where the stuff has come from, a little bit further, this table summarizes in a more easy to digest way by the potential types of sources. And we've done this by inspecting each compound individually and figuring out what is the single most likely source of that compound. And it shows us that it's actually the coach which has particularly high exposures to these personal care products, but also quite high exposure to combustion emissions as well. Now that leads us tentatively to suggest it's actually a relatively small interior volume of the coach combined with quite a lot of people means that you're smelling other people quite a lot. And perhaps the ventilation on this coach is not as good as some others, and so lots of combustion emissions are entering from other vehicles on the road. Now, an interesting one, if we compare the two types of car, the diesel car and the electric car, actually the diesel car has much lower VOC emissions than the electric car. Now, in this case, we put this down most likely to the age of the vehicles and the quality of the vehicles. The diesel car was older, but an older premium car. Now, why that matters is because it's older, a lot of the VOCs from the interior materials have long since evaporated off, whereas the electric car was brand new. Also, the old car was a premium car and the electric car was a mass market electric car. And this leads us to think that the quality of the ventilation system was actually superior in the diesel car, even though it was older. And that combination means that the exposures in that diesel car were, and of all the powered transport, the lowest emissions overall. The electric diesel hybrid train is notable in it had particularly high plastics emissions, which are most likely to be from the interior materials used in the train. But this is all logical deduction using best available information. These conclusions cannot be, on this first pass type research, absolutely conclusive on these sources. So that's the VOC results. Moving on to the particles and carbon dioxide, and I've got 5 slides, one for each day, which reflects the different journeys taken. So the first day was going straight from Paddington to Oxford via diesel electric train, and then a combination of bus and walking from the station to the city centre. The graph on the right is the time series with particle number concentration on the left vertical and particle mass concentration on the right vertical. And as you can see, it's annotated for key events. And the train is a hybrid train. It is essentially electric most of the way to Oxford, and then it switches to diesel about 10 to 15 kilometres outside of Oxford. And some things to note. Well, firstly, it shows how transient these sort of exposures are. There's long periods of the journey which have very low particle exposures and interspersed with sharp spikes at certain events. Generally speaking, interestingly, being on the train has lower exposures just by way of background exposures to the traveller compared to the bus and foot leg within Oxford city centre. Now, that may well reflect the background emissions in a city versus the train zooming through the leafy countryside. Other than that, if we look at the spikes, the most notable thing by far is they are around stations. The highest are getting on and off the train, where obviously the traveller is physically getting off the train. But also just when the train is stopping in other stations, even if you as the passenger stay seated, opening the doors lets in a waft of particles, and that can quite clearly be picked up by the traveller. But it's worth noting this train, you have those spikes, but the ventilation system, once the doors are closed, clear up the problem quite quickly. One final thing to note on this one is that, and this probably doesn't come as much of a surprise, is smoking is bad. It is clearly notable that smokers have to be patient during the journey, and as soon as they get off the train they light up, and so you then walk through a waft of other people smoking, and that creates particularly high spikes, and that's that green, the pale green spike towards the end of the journey is walking through a waft of cigarette smoke getting off I think it was getting onto the bus. So that was day one, and we can trot through the others a little bit more swiftly. So the second one was same point-to-point journey on 2 diesel trains, but taking an indirect route via the London Underground first, and then changing diesel trains at Basingstoke. These were older rolling stock than the first one, but a similar pattern is seen. Certainly on the interchange at Basingstoke, and then the stops along the way. Although in this case, relatively speaking, the exposures at the interchange were higher than opening the doors of the train at the intermediate stops. What's new and different about this compared to the last one is the London Underground route, which is obviously electric underground railway, which has extremely low particle number emissions, but very high relatively particle mass emissions, which points to bigger particles. And these bigger particles are likely to be, so there's no combustion emissions, for example, and that's one major change. So there will be material which is being, abrasion of the tracks and other large number of humans in a small space, likely to be causing that level of larger particles. Third day was going by coach. Now this involved getting from Paddington to Victoria on the London Underground, and we saw a similar pattern of elevated particle mass emissions, but there was a particular spike when on the platform at London Waterloo of particle mass. May well be to do with when the train entered the station. Then there's high emissions, both of number and mass transfer to the coach, which is an area of quite a lot of combustion emissions. And then you have the coach doing its long, slow journey with stops along a motorway. So it's exposed to combustion emissions from lots of vehicles and opening the doors, a recipe for higher, particularly of the fine particle emissions from combustion rather than the coarser emissions. Again, then one arrives in Oxford, gets off the coach, you step onto the high street and you're stepping into, again, a plume of cigarette smoke. And I see noted in the chat maybe a reference to vaping. I'm sure there was some vaping included in that as well, but not just smoking, but also essentially cooking emissions. They're often, whether it's kebab vans or local cafes, clustered in the city centre, exhausting those cooking smells may well be contributing. They were certainly observable and were recorded by the traveller doing this, doing these measurements. Moving on then to the 2 passenger cars. So day 4 was the battery electric vehicle. Now this went from Paddington to Oxford out of the centre parking, and then with a on-foot journey to the city centre. And the most notable thing here is the biggest single spike of emissions was getting into the car at London Paddington. Once inside the car, and these axes have been scaled, but actually these are relatively low emissions compared to the other days. The particle mass and particle number were kept at pretty low levels. I mean, not still measurable, and a function largely of combustion emissions from other vehicles getting inside as driving along the M40. Once parked and out in Oxford, then you saw walking along, there were actually more exposures to particle mass emissions than particle number emissions, and that probably was a function of the route taken through the medieval streets of Oxford. And finally, day 5, so that was taking the older premium diesel vehicle, and this one we just simply did door to door. So in at Paddington, out in Oxford High Street. And this had the lowest overall exposures. Maybe distorted, and this must be noted that in the middle of the journey there was some rain, which is noted on the chart, and where you can see it suppresses both particle mass and particle number. Shortly after the rain shower, we hit some congestion, which is noted on the chart, and where we see then a big spike relatively in particle number emissions, which helps give credence to the idea that these spikes in PN emissions when on the road are due to combustion emissions. And you can also see, as getting into the outskirts of Oxford into the city centre, again there are lots of rapid peaks of particle number as well, which probably correlate to the car you're stopped behind waiting at a traffic light. So that's the individual detail. I think it gives a good flavour of what we're seeing and the granularity of this information. And while we can't be absolutely certain in some of these conclusions, it's I think pretty a reasonable level of confidence. So if we take all those 5 days together and look at the summary by mode of the particle number, concentrations, particle mass, and I've added in the carbon dioxide as well. I'm not majoring on this in this presentation, but that is the interior CO2, which is a proxy for the freshness of the air. So essentially, where you see CO2 increasing, that is likely to be poor air exchange rates and correlates with stuffiness and less passenger comfort. Obviously, CO2 at these levels is not in any form of danger, except maybe causing a little bit of drowsiness and not that comfortable a journey. So this list is ranked by the PN concentrations, and that puts the diesel train and the coach at the top of the list, with the diesel train particularly high, and that was driven by the station and the interchanges. If we were just looking at the PN in the diesel train while it was going along with the doors shut, it would be well down the list. For particle mass emissions, the London Underground is standout, more than double over any of the other modes. And CO2, the worst one was actually the hybrid train. And that is likely to be to do with the design of the ventilation system or the settings it was operated on. The motivation's unclear, but that's what we clearly observed. So then overall, just my high-level takeaways from this is that trains are mixed. They're generally good when you're shut away inside them, and particularly going through countryside, but they're relatively bad in stations at interchanges. in fact, when we calculate it, if we look at what the total exposure of those train journeys is due to just those stations, it's between 18 and 29%. So a decent minority of the total emissions are in those relatively brief periods in just getting on and off. It's not even the station stops; it's getting on and off the trains. The hybrid train also had a notable exposure to VOCs, and including the aromatics compounds, and that may well be to do with the interior materials used. The coach was, it's slow and subject to traffic pollution, and it has the Achilles heel of trains as well, in that it has station stops and interchanges. So that is the most challenging scenario across all these different journeys. And in both the trains and coach, plastics from interior materials, or the seat covers and the carpets and the like, were seemingly measurable as an exposure to the traveller. The underground travel was generally very low for particle number, the ultrafine particles, but those larger particles are likely to be shavings of metal from the tracks and the wheels, and possibly also human detritus as well. Cars are generally good, driven mostly by their point-to-point, and they're quick. And we saw, so much of the relative exposure was getting into the vehicle, getting into the car at Paddington. So once you're sealed away in the car, if you can go in your seal pod quickly, that does lead to the lowest emissions. It doesn't mean, if you have a poor ventilation system, you will still suck in combustion emissions. But nevertheless, that does stand out. But it does show what type of car you use and what ventilation settings you use does have a material impact on your total exposures. Walking and cycling, we clearly observe, and that this is in city centres, and understandably, therefore, you're seeing big spikes as you pass by a dirty old bus, or not that Oxford has any dirty old buses anymore, or dirty old trucks. You do get big spikes, but the amount of fresh air in between and the level of respiration as well helps massively dilute those exposures. And overall, walking and cycling, not in every case here, but generally comes out as the least polluting method of transport. The obvious restriction is that the range you can go by either of those modes is obviously smaller than, in practical terms, than others. So implications of this and pointers for further work. Firstly, journeys involve high variations in exposure concentration. So that means it's not as if we're trying to, the optimal thing is to try and reduce concentrations while sitting on a train. It seems to point, we need to try and first of all tackle the spikes. And that points to, can we clean up stations and interchanges? And maybe that's more of a priority than upgrading rolling stock. Can we, on the coach, improve the filtration and the ventilation on the coach to stop the ingress of combustion particles and to keep the air fresh there? On cars, logically, other considerations aside, you want cars to be able to go point to point to protect the passenger as much as possible from the outside world. But obviously that comes subject to many constraints, including congestion and costs and quality of the urban environment. But that's what it logically points to. How can we extend, if possible, the range of active travel, making it do longer distance journeys, cycling, for example? Now, London to Oxford is probably pushing it too far, but the degree to which we can allow longer range in cycling particularly would definitely be helpful. And then if we can restrict smoking and food cooking at interchanges, so we don't always have to walk off a coach into a plume of smokers and burnt toasties, might actually be be a relatively easy way to make traveling more pleasant and reduce the exposures. So what do we need to do next? Well, first of all, we need to reproduce the results and take this as a first pointer of where there are specific problems and where we need to delve in detail. This was a scanner of the horizon, and now we need to narrow it down, focus on those problem areas, opportunity areas, and then conduct reproducible research to make those results a firm basis for any policy interventions. Before finishing, I just wanted to mention, and while this exact method wasn't employed here because it hadn't been finalized yet, recently has been published a new standardized methodology called CWA 17934 for measuring in-cabin pollution. It was the product of SEN Workshop 103, which I was the chairman of, and its focus was on the measurement of the ingress of particles into the vehicle cabin from outside into light-duty vehicles, and also the build-up of CO2, essentially looking at the trade-off between those two. If you use recirculation settings, you might reduce particle ingress, but at the cost of CO2 build-up. This is all in real on-world test protocol, and the metric used is the integrated ratio between the external and internal concentrations. And what we found was a very interesting finding, which was for any given vehicle and a given ventilation setting, that ratio would converge over about 30 minutes to a consistent characteristic value for that vehicle and ventilation setting, independent of what test route was driven. And that is a really interesting finding, that you could come up essentially with one number to characterize a vehicle on a ventilation setting, almost irrespective of what was going on outside. And we've proven this to be repeatable, and we will start publishing results based on this soon. So this may well be a method that could be employed on public transport as well, because the showing it converges to that consistent value collapses the dimensions of complexity of this problem. And it allows comparison between different vehicles on a fair basis, but also comparison between different filters on the same vehicle, and can help show how just literally simple interventions like changing your air filter into the cabin can make a material difference to your particle exposure. So on that note, thank you very much for listening. As always, we appreciate your time, and I will I would like to open it up to questions. So I'll just pause for a second while I consult the questions list, and then I'll tackle some questions. Thank you very much. Okay, so tackling question. There was just one question early on about the diesel car being used and whether it had a DPF or not. Well, it did have a DPF. It was a Euro 5 diesel vehicle. But having said that, I don't think that one way or the other would be particularly material to the outcome of the results, because the pollution getting into the car was not generally from its own tailpipe. The particles are getting in from other vehicles, and especially the vehicle immediately in front of the car. That's what we've seen in other work we've done, and it explains why combustion emissions are getting in to the electric car, for example. So yes, it does have a DPF, but I don't think that it's so relevant for these results. Have we ever done this research on air travel? We have, actually. I'm a little cautious as to what I can say. We have done VOC monitoring on aircraft, and not a huge program, but some. And the motivation was originally the talk of high fume events in certain circumstances, because of the bleed air coming through the engine and being warmed up by the engine. There's always been the risk of fumes from lubricants in the engine getting into the cabin through the bleed valve. And this is seeming to be well documented, although quite controversial. On the air journeys that we have measured, which were primarily long haul ones, that's not what we observed. We did not observe any fume events. Now, possibly because the sample size was relatively low, we wouldn't, because we just didn't do enough travel. We didn't, these are intermittent events, and we may just not have coincided with one. However, what we did pick up were two things. Firstly, the some sort of plastics, interior materials concentrations, but more starkly, we think we were picking up fumes from de-icing, de-icing the exterior of the vehicle and that getting into the cabin. That said, I would very strongly say, that overall, the concentrations of VOCs we were seeing inside these aeroplanes was, relative to other modes, very low. It seems that the ventilation systems of the aircraft that we went on are very good. Now, these were relatively modern airliners, modern long-haul airliners, but what was striking compared to what we've seen this morning, actually the concentrations in the aircraft were low. Okay, well, what do you think might be reasonable background numbers for PN and VOCs for human exposure at rest in a living room, walking in rural Oxfordshire? Good question. So, I mean, we would normally consider completely fresh air on particle mass, on particle number, to be maybe in the 2,000 particles per centimetre cubed. But it is an interesting debate, because if you're in the middle of the countryside, that would generally be considered as beautiful background fresh air, but actually won't necessarily be free of particles. If it's in farming land, it may well be that there's exposures to quite a lot of PM from whether it's dust or whether it's secondary organic aerosols from reacting of chemicals used on farms. So what is actually background is an interesting philosophical debate, but as a rough rule of thumb, I would say, in the low thousands of particle number per centimetre cubed, and in the sub 1 on the particle mass per metre cubed. It's quite a difference between underground stations and the train. So if I understand that correctly, between the underground stations and the train stations, it was really quite different. The underground stations were dominated by spikes in particle mass, bigger particles, whereas the train stations were, well, both, but with a very much skew towards the smaller particles. And that is, in the underground stations, we think the rail abrasion and the human debris gets stirred up. There are no combustion emissions around, whereas in the train stations, you've got a heady mix of you've got a bit of that in terms of rail wear, but you've got diesel combustion emissions, and you've got all the food stalls burning food as well, all in a confined space. And and a person can testify to certain bits of Paddington Station being that. So on the average, particle size would be a big difference between those two locations. Or controversial question: is there any read across to exposure to infectious diseases, flu, COVID, etc.? Well, I think there has to be. There has to be, and a COVID virus. Let's take that as the current one. A COVID virus is, I think, about 300 microns in diameter. So it is very much. It's not in the PN zone, but it's in the particle mass zone where we would pick it up. I think it's the CO2 numbers which are possibly most relevant, and that is a measure of air freshness within and the air turnover within these confined spaces. This is possibly more important than the particle numbers. A lot of those are about particle ingress from outside, combustion emissions getting inside, whereas the CO2 is a good measure of how quickly that air is being turned over, filtered, cleaned, and that's why the hybrid train, with having relatively high CO2, is one where I would be looking at that further and saying, actually, that ventilation is not as good as a lot of these other transportation modes. Can we do something for more rapid air exchange, which could have a material impact in reducing transmission of airborne viruses? So I haven't probably given CO2 the CO2 measurements the justice they deserve in this presentation, but that's how I would start approaching it. And commonsensically, well, we cannot conclude from this that everyone should abandon public transport and go by private car because it seals everyone away. That's not realistic in any level, least of all for environment and congestion. So we have to make public transport work. We have to make public transport as comfortable as possible, as healthy as possible. And so being very attentive to, how do we keep the air fresh when you're putting a lot of human beings in a narrow space all side by side for a long period of time. And the air exchange rate and filtration is probably key to that. Are there any plans to repeat this looking at NOx? Potentially. I mean, it is an area of further research that we could do. The issue is, one has to question whether the level of NOx emissions inside vehicles are at levels now that are of any concern. And we've not observed particularly high concentrations of NOx inside vehicles. That's why we've not prioritized it in the same way as particles. Also, with diesels getting cleaner and cleaner, switch back to gasoline, switch to electric, that may well prove to be a declining problem. But it's certainly been the case on other research where at certain parts in a train, you can observe much higher NOx concentrations than in other parts of the train, depending on where the plume of diesel is settling. So it can be higher pollution towards the back of the train than near the front. So we would like to look at it. I'm not saying it's not a problem, and if we can find a project to do it, we would be certainly keen to. Okay, moving on. I've travelled on the Oxford to London train many times. Interested in the apparent increase in background level of PN. What was the direction of travel on that day? It was from London to Oxford. All these journeys were from London to Oxford. And yes, it does switch to the diesel near Didcot, that's right. So when looking at the chart, and I maybe have to cycle back to the chart. So this would be, this period here would be the period where the diesel train would be kicking in. But we think actually the emissions here were dominated much more by the getting off the train at Oxford and then switching to the bus than it was by any exposures on the train itself, just looking at the timestamps. As a matter of perspective, are exposures at home higher or lower than on the journeys? That's a really good question. And we haven't done detailed studies of home pollution. And people who have are the National Air Quality Testing Service, NAQTS, that have provided the analyzers, and they may well be able to contribute some thoughts on that. What I do know is that it very much depends upon what's in the room, what products, what things are off-gassing. For example, if you have a new carpet put down, that for a period will have some very high VOC emissions, or a new sofa. If you have or if you're in near a kitchen will have all sorts of combustion emissions in it. So it's in a sense analogous to this. The concentration levels are very volatile, pardon the expression, depending on the location and how many people are in the house and what you're doing and time of day and all that, and the heating system is on. The same goes for offices as well. Offices, again, it very much a function of what the interior furnishings are. In that case, then where you have air conditioning systems, ventilation system, the quality of that and the air exchange rate there, that's probably the dominant thing as to how good an office environment is. Obviously, that doesn't exist normally at home. So then it is more passively about what the materials you've got in the room. How are these particle results comparing to previous years? Well, we haven't done this equivalent thing 5 years ago, unfortunately. What I would, my educated guess would be that generally speaking, the trend in tailpipe emissions is down a bit, and the trend in air quality, pollutant concentrations in the air is down, particularly of particles. And even NOx is beginning to come down, less so than may be expected because of the various manipulation of the official system that is well known around tailpipe, and also the ambient particle levels. The sources of particle emissions are from things like home heating and agriculture and industry, and also tire wear emissions, things which are not directly linked to, which aren't linked to the vehicle tailpipes. So there is a gentle downward trend. I think also our standards of what our expectations are have gone up a lot. So people are more sensitive generally to smells and other unpleasantness, either in public transport or on stations. People are more sensitive to walking through plumes of other people's smoke. So while we may perceive that the problem may be getting worse, even actually, I suspect the problem is gradually improving naturally. But that doesn't mean that's a call for no action at all. By looking at these spikes, they are the obvious places for intervention where we could make some big differences. We're certainly not in the clear. We do not have completely clean air. Walk around Paddington Station, the problem is not completely solved. But let's go and try and tackle those peaks, because they're the problem, even though if the underlying trend over time is gradual improvement. How do these vary in winter versus summer? What's the seasonal trend? Well, again, this was all in May, so we we're not able to do a seasonal comparison. That would be a very interesting thing to do. Lots of different factors. I mean, obviously, in rainy periods, clearly rain suppresses particles. That's undoubtedly true. In terms of VOCs as well, there are many factors affecting. So on hotter days, there will be higher rates of off-gassing of VOCs from materials, for example. Also, the season will affect what's going on in the natural environment in terms of growth of foliage and or farming activity, and how that is releasing VOCs and particles and secondary organic aerosol formation. That is very strongly correlated to those seasonal patterns. One thing we didn't look at here at all was atmospheric ground level ozone directly, which again is a highly seasonal or dependent on weather conditions effect. It is relevant though, and the VOCs are relevant to that, as they are one of the key precursors to the ozone formation. So the more VOCs we're seeing emitted and off-gassed is relevant to that. So I guess this speaks to, there are many other dimensions I'd love to pursue. That this would be a great basis for doing it, and would be very much open to working on other projects. Particle concentrations are recognized to vary by carriage location on the train, proximity to the motor. Yeah, that's absolutely true. And the Rail Safety Board has done some excellent work. There's some really fascinating reports done, and to me that just goes to show that how sensitive certain things, your exposures are to certain choices as to where you sit in the train, or choices as to whether you go on a direct train or you have to change, or on a train that stops at lots of stops or just goes point to point. Or whether you have to do a leg on the London Underground before you get on the coach. All those sort of things which sound like detail, sound like secondary detail, actually might be much more important in your total exposure. And so from a passenger point of view, what do you do? Do you just sort of resign yourself to its pot luck? It's difficult to know how you would get that information in real time to make any decision. So probably the optimal thing is for the operators, the authorities, to study this, to understand where those hot spots are. So, if you sit in carriage 2, you're going to get a lot of knocks. Understand where those hot spots are and tackle those on a tactical basis. Eliminate those hot spots. And it's analogous to, how really the ambient NOx emissions have been dealt with in city centres. It's essentially been, a lot of it's been about tackling hotspots by restricting traffic, redirecting traffic, charging mechanisms. So rather than going for system level revolution, it's much more tactical. And maybe that is the optimal thing to do, because what we don't conclude from this piece of work is that all the train rolling stock is rotten and needs to be replaced by the new latest stuff. That does not come out from this. It is more about that we need to think about it at the whole system level, the whole journey level, and then focusing on the spikes at the hot spots. So we don't waste money doing things which are actually going to might sound nice and shiny at getting new trains, but actually might not be the thing which has the biggest impact on the human exposures. There's a number of questions about calibration of the equipment, and also the lower size, or the range of particle sizes for particle number. On that last point, it is essentially 15 nanometers. So the detection efficiency is 50% at about 15 nanometers, which means it sits roughly halfway between the current 23 nanometer lower size cutoff for tailpipe regulations and the proposed 10 nanometers. In terms of calibration on the CO2 side, we were regularly calibrating against a known concentration of CO2. So the value should be both accurate, but in any case, they are definitely relatively a correct relative statement between the different modes of transport. But it's also worth citing other work we've done on testing passenger vehicles, because the point was made about multiple occupants of vehicles leading to potentially much higher concentrations of CO2, and we certainly see that in a passenger vehicle. If you have it on recirculation setting and you have one person in the vehicle, it can easily get up to 1,000 ppm within about 20 minutes. But if you have two people, it will rise pretty much at double that rate. And you can imagine if you have a full car, you can get up to some thousands of ppm over a journey. So using exactly the same equipment, same calibration, same approach, you do see rapidly rising CO2 in those cases. What I conclude from this data is that, yes, there are some relative differences between the modes, and some are slightly stuffier than others, but there are actually no cases in which the CO2 goes dramatically high. On the calibration of the particles, that is a simpler with zeroing of those, regular zeroing of those through the testing, zeroing on clean ambient air. So picking up some of the other questions, looking down, there's a reference to some vehicles like Tesla or high-end cars can have very good filtration. We actually have tested well over 100 different passenger cars using this essential methodology. And firstly, it is, if we talk about the rate of ingress of particles, there's a factor of about 3 difference between the best and the worst. And the very best we have ever tested is a Tesla X using the bioweapon defense mode. Which it needs to be said is a version of recirculation. So naturally you would expect it to be quite good, but also with potential for CO2 increases. But that was near complete filtration on our on-road route. There are, it should be said, some other vehicles which come quite close to that, even without the really extreme strategies that Tesla employ, but that does, the Tesla X does currently sit at pole position in the testing we've ever done. Question: what kind of filtration systems would efficiently clean the ventilation intake air in passenger vehicles? Well, most commonly, these filtration systems have particle filters in them. We are currently doing a program which, using the new CWA methodology, that compares the relative effectiveness of different filters, premium, budget, mid-market, and different types of woven, non-woven filters, to see which ones do have the most effectiveness. One thing to note is we have actually seen that the ratio of inside and outside is relatively independent of the size distribution of the particles as well. So despite the fact that filters have different filtration efficiencies at different sizes of particle, the mix of particles in the air seems to be such that it doesn't affect the ratio in any dramatic way. In terms of scrubbing other things like VOCs, some vehicles do have activated carbon filters. We haven't tested those as yet, so I can make no comment about the efficacy. In terms of scrubbing other things like NOx, that becomes really difficult without some form of reagent, but also the concentrations in the air are quite low to start with. Back on CO2, actually, a useful comment about over 1,000 ppm of CO2 would surely affect the ability to think clearly. My answer to that is absolutely yes. And it's really interesting that we regulate the tailpipe very tightly, yet vehicle interior air quality is, to all intents and purposes, unregulated, despite the fact that CO2 can rise above, well above 1,000 if you have multiple people in a vehicle. So why aren't we falling asleep at the wheel or crashing all the time? Well, it may well be that actually our accident rate is higher than it should be because of that. But two other reasons I would say is generally those high values are only seen on recirculation, and most vehicles default to the fresh air mode. But also, if you start getting up to very high CO2 levels, you see other things in the vehicle like condensation, or it gets really stuffy or smelly, which leads you then to switch ventilation system or even potentially open the window. So our theory is that that there are other triggers which lead the driver to do some intervention before the CO2 rates get to dangerously high levels. But that, hands up, that is an educated theory rather than anything we've proven so far. Next question. Do you expect the conclusions drawn from this pilot to be different from other gaseous pollutants? And yes, I think that is true. And what we can see, and nitrogen dioxide specifically stated. I mean, I think what we can see even within the scope of this presentation, that the patterns between the different pollutants are quite different. So the VOCs is very much to do with who else is with you in the vehicle and the fabric of the vehicle, whereas particle mass is a function of some very particular sources, and particle number is other quite distinct sources, combustion emissions. So if we were doing NO2, or we were doing formaldehyde, or we were doing any of these other, carbon monoxide, each would have very different characteristic results. And that's why we've started with the ones which we think are potentially the most significant problems to date. Okay, let's look down the list a bit further. So for underground particle mass, your conclusions suggest to clean platform stations regularly, and this means that the majority of concentration is probably due to resuspension rather than direct daily emissions. In your view, would any type of air filtration be as effective as cleaning surfaces? Well, to my knowledge, within the London Underground, there is regular cleaning of the material that collects underneath the tracks, which is a lot of fluff and other material. And they clean it not from an air quality point of view, but actually from a fire risk point of view, as that it can actually be very combustible material. So there is a regular program of doing that. And I think every night. Now, whether every station is cleaned every night, I don't know. And there may be people on the call who can fill me in. However, there is regular cleaning, which means, yes, there will be resuspension, but a lot of it is freshly deposited material abraded from the track or from humans. So probably the solution is some combination of air filtration and more regular cleaning. Probably given the budgets then become an issue. We need to find which is the most economically viable way of creating that cleaning, and whether it is air filtration or cleaning. That I do not know. Okay, let's looking down. So. What else have we got? There was a question earlier. Someone asked about what this says about infectious diseases and COVID, for example, and whether this, what implications this might have. And the COVID virus, I think, is around 100 nanometers, maybe a little bit larger. So it's absolutely in the range of these measurements. And it has to be said that this does show being in a confined, sealed space with lots of other humans in very close proximity through the VOC measurements that we are able to pick up perfumes, shampoos, plastics, even sort of plastic from plastic bottles from drinking water, for example, as well as from carpets and other materials of the inner fabric of the vehicle. So this does show that how relatively low concentrations of nasty things can transmit and around vehicles. And so it does point to the importance of ventilation systems in these areas, not just from creating comfort, but also reducing those health exposures. And so as an intervention to reduce transmission generally, not just of COVID, but flu and other transmissible diseases, the value in the air exchange rate is actually potentially really quite significant. So between that and cleaning up these nasty hotspots on train platforms, those may well be the better ways of addressing this, rather than going to replace the whole rolling stock on trains, for example, or the whole new coach, replace all the coach fleet. Maybe simple upgrades to the ventilation system and addressing the nature of the interchanges and the stops may actually have a much greater return on investment. What else have we? Are there any other modes of transport that you're looking at monitoring? Well, yes, and in fact, we have done a little bit on aeroplanes. Aeroplanes is undoubtedly somewhat controversial area around fume events, and there's been various stories in the press over the years about pilots having certain cognitive effects of apparently organic compounds through the bleed air, i.e. so the fresh air being brought in through the engines to warm it up, but organic compounds from the lubrication getting in through that system. And this may or may not be true. I don't think it has been conclusively proved one way or the other, and there's campaign groups. But what we've done, we've already done some experiments on some long haul flights with sampling of VOCs to see if we could pick up any hallmark of these fume events. And the answer so far is no. We have not found. This is relatively small sample sizes so far, so certainly not a definitive conclusion. But what we are picking up is two things. Firstly, the VOCs we are picking up are mostly from, apart from the personal care products of other humans, we are definitely picking up the hallmark of the interior furnishings of the plastics and the carpets, etc., from the internal furnishings of the aeroplane. And these are generally would have been relatively modern, long-haul aircraft. So we're definitely picking up that. But the other thing we see is that the filtration and the air exchange rates seem to be generally excellent. So it may be that even though in COVID, mass panic and restriction of air travel, it may actually be within aircraft were some of the cleanest places to be, rather than some other modes of transport. And certainly other research I've seen is what the main vector of transmission in aircraft seemed to be from dirty tops of seats, where people were getting in and out of the airplane, rather than from the actual airborne respiration and air circulation. So yeah, so we are potentially going to do more in that area, and any other areas really, essentially, where people are moving around in confined spaces is within our sites. Next question: if we tested this out by cycling 65 miles from London to Oxford, would we get a high level simply because of the large amount of time and high inhalation of air? Really good question. Really good question. And my back of the envelope calculations, so that will be my hypothesis, is that it will actually be very low average exposures. And the reason I say that is, yes, because it'll be arduous, there will be high inhalation of air, but a lot of the time the cycling will probably be through relatively clean air, and for a lot of it actually through the countryside, which is a lot of the distance, will be really very clean air. That may not be the experience of the cyclist himself, herself, because you'll very much experience plumes of dirty, tailpipe and other pollution, but it'll be sharp spikes of it, and then long periods of cleaner air. So that's my theory, and it mirrors, as you can see from the results that we saw for walking and cycling in Oxford. We had reports from the people conducting it, of all the different smells and plumes that they were experiencing, and it sounded quite bad. But when you actually looked at the numbers, that was the thing which stuck in the mind. But actually, the vast majority of the time was in very clean air. Okay, just looking through and appreciating all the other comments coming in, there was a question earlier that might be useful, which was around what are the expected background concentrations of particles and VOC. So to put in context these, and we always use the word background, but it's quite tricky actually to define. Well, there's lots of different sorts of backgrounds which actually can have quite dramatically different values. So the countryside you may psychologically think that that is very clean air, but if it's near particular farming activity, there can be high particles from dust. There can also be VOCs from certain chemicals being used, or secondary organic aerosols being formed. So those sorts of country locations are not necessarily clean air and a good definition of background. That said, a general experience would be, really clean air would have maybe 2,000 particles per centimeter cubed, and the particle mass would be down in the very low, 1 per unit per meter cubed, something like that. But it is somewhat variable, but that would then in context show that what we're measuring is multiple times greater than that sort of quote clean background. Okay, I think there's a final, maybe the odd final question coming in, and then we will wrap up. So do put any last questions in. I think we might well have covered everything, materials. So if I haven't covered all your points, please do get in touch afterwards, and we'll be very happy to discuss. There will be a recording of this, so the slides and the recording will be available. Please do get in touch, and I will take that. There is one last question which I will take, which is, how do you know that expensive cars have very good filtration? Well, that isn't true as a general statement. That is not. We have seen plenty of expensive cars with actually really quite poor filtration. All I've said is that the very best that we've had so far is the Tesla X, which is a very expensive car. We've also seen some small cars with relatively good filtration, and actually, one of the single biggest levers you've got to clean it up is just a good filter, which may be a £50 item. So it is not the most expensive component, and you can choose to put a better filter in it. So it doesn't correlate very closely with vehicle cost. What does bias it perhaps is on the CO2 side towards expensive cars, where expensive cars typically have a larger interior air volume. And so that will mean the buildup of CO2 will be slower than if you have a super mini with 5 people stuffed inside it. So, but this is all work in progress. I imagine I will be presenting more results of this as we go next year. So thank you very much all for attending. Really appreciate your time and your interest as ever. Thank you to everyone at Transition, Suzanne, James, Bill, Carl, everyone for supporting this. I think it is just a start, but hopefully it's proved stimulating, and see you on a future webinar. Thank you very much.